Okay, let's take a look at some example problems where we have mono-substituted benzenes, and we want to know what the effect of those substituents are going to be in terms of their activating and directing properties. All right, so this first problem is a little bit long, but I do want you to be able to explain why a group is activating or deactivating and what the directing effects are going to be by looking at the resonance structures of both the starting compound and the sigma complex. So first we want to use resonance structures to explain whether this compound is activating or whether the substituent is activating or deactivating, and so whether the ring is activated or deactivated. So we could first make a case for induction, right? I've got this nitrogen some distance away from the aromatic ring. That's going to have some modest induction effects, but I think resonance is going to be the biggest contributor in this case. And so we should be able to predict at this point that this is going to be moderately deactivating because I have on a carbon adjacent to the aromatic ring, I have a pi bond with a more electronegative atom. And so the reason this is going to be deactivating is because it's going to be electron withdrawing, because I can draw the following resonance structure. And now, with this positive charge on this carbon, I have an allylic carbocation, and so then I can draw then this resonance structure. In the interest of time, I'm not going to draw them, but then I can also, move the positive charge here and then here. And so I'm going to have three different resonance structures of my starting compound where I have a positive charge introduced to the aromatic ring. So this is an electron withdrawing group, which means it's going to be deactivating. Now I can't just tell from the resonance structures what the strength is, but if you remember, halogens are the weak deactivators. When I have a pi bond, including a more electronegative atom than carbon, adjacent to the aromatic ring, this is an example of a moderate deactivator. If I had a nitro group or a positive ammonium ion or a methyl group tri-substituted with halogens, those would all be strong deactivators. So this is an example of a moderate deactivator. Now to consider the directing effects, I want to consider the resonance structures of the sigma complex. Now again, we should be able to know that when we have moderate and strong deactivators, these are going to be meta-directors, but let's draw the resonance structures of the sigma complex to show that. So I'm starting with this compound. If I go to add something in the meta position, I'm going to add a group here. Let's make it a halogen for simplicity. So to get the sigma complex, I'm going to put a positive charge here. And then, again, I'm going to save a little bit of time. I can then move this positive charge around the ring in the sigma complex, where the positive charge is going to be here, or here, or here. And so I don't get any particularly stable or particularly unstable resonance contributors for the sigma complex when I add in the meta position. On the other hand, if I try to add this to the ortho or para positions, so now this is going to give me this sigma complex. And so this is an example like we saw with the group where we looked at the nitro substituent more closely. We have the positive charge directly next to the electron withdrawing group. This is a particularly unstable resonance contributor that I'm going to get when I try to add, in this case, the halogen to either the ortho or the para positions. So in this case, the addition of a group in the ortho and para position is particularly unstable, and so that's what makes these deactivating groups, with the exception of the halogens, meta-directors. All right, so a similar type question, but we don't have to go through and draw all the resonance structures. They just want us to make the predictions. So in this case, I have a lone pair on an atom directly adjacent to the aromatic ring. So that's going to make this ring activated. But when I have a pi bond on a neighboring atom, because I can draw this resonance structure, I get resonance that's outside of the benzene ring, which makes this a moderate activator. Compare this to something like where I don't have any resonance outside the ring. This would be a strong activator. The presence of this group here is what makes it a moderate activator. And like all activators, this is going to be an ortho-para director. Okay, so in this case, they want me to predict the products of a reaction when I treat this with a mixture of nitric acid and sulfuric acid. And so this is going to give me nitration, so I'm going to add an NO2 group, but then I need to decide where it's going to end up. So this group is a moderate deactivator, right? I can draw the resonance structure. We're going to end up with a negative charge on that oxygen, a positive charge on that carbon. I can then draw this resonance structure, so it's electron withdrawing. And the electron withdrawing groups are going to be meta-directors except the halogens. Of course, this is not a halogen. And so I'm going to add my nitro group in the meta position. And there's only one product in this case, so I don't need to worry about the major or minor products. All right, here's a similar example. In this case, I'm starting with phenol. I'm treating it with chloroethane and aluminum trichloride. So this is going to give me Friedel-Crafts alkylation. So this is going to add an ethane to my benzene ring. I have a phenol. In this case, I have lone pairs on an atom directly adjacent to the aromatic ring. There's no resonance outside of the ring, so this is going to be a strong activator. And so a strong activator is going to be an ortho-para director. So I should get two products, and then we need to consider which one is going to be the major product. And so the factors that we need to consider are steric hindrance and just the statistics. There are more ortho positions than there are para positions. In the very first example that we did, we saw that when we were adding a nitro group to the methyl substituted benzene, that the steric considerations were not that important, so we got mostly ortho because there were two positions we could put it. I think in the case of Friedel-Crafts alkylation, in most other cases, steric hindrance is probably going to be the major effect, and so we would expect that this would be the major product. All right, one more example. So we're treating bromobenzene with a mixture of bromine and iron 3 bromide. So that's going to give me bromination. Now, the bromine group is going to be weakly deactivating, but it's still going to be an ortho-para director. So we would expect our products to be these two. Again, steric considerations are generally going to be more important, so we would predict this to be our major product.